introduce this afternoon's seminar, I have got a couple of housekeeping notes. The hashtag for this afternoon is human tech, but obviously if you're going to tweet, please make sure your devices are on silent if you're not going to either switch them off or make sure they're on silent. We have another lecture taking place straight after this one, so if you're not registered for that and attending it, please could I ask you to exit quite swiftly so that we can ensure we get the other audience in time. We wouldn't normally do this, but it's very tight timings today. So to the seminar itself. From sensors on the body that transmit medical information to smart parking sensors that enable people to see what parking spaces are available, this technology seems to be everywhere now. This afternoon's experts, Professor Marta Kwiatkowska and Dr. Niki Trigoni, will be giving their views on where sensors could potentially take us in the future, where they could be most successful and where the challenges are. So without further ado, I hand over to our speakers.
Good afternoon. I'm Marta Kwiatkowska. I have to compliment the person who introduced me for the pronunciation. It's quite a tricky pronunciation. I happen to be born in Poland, but I've lived here for nearly 30 years. My husband is English as well, so he sometimes writes down for me the English phonetic pronunciation of my name. What I'm going to do is I'm going to start this afternoon by giving you the context for ubiquitous computing. I'll explain what it is, and I'll also say something about the trends and challenges. And I will be followed by my colleague, Niki Trigoni, who is going to talk about a specific and a very exciting aspect of her research, which also belongs to this field. So before we start, I would like you to think and consider a typical urban scene. For example, this could be London, it could be San Francisco or New York, and ask yourself the question, where are the computers? We know we use computers all the time, but where are they? Well, once upon a time, back in the 1980s, if you were born at that time, computers were very large and they occupied large rooms, air-conditioned. They were attended by operators in white coats, and you had to communicate with them using punched cards. Anybody here knows what punched cards are? That's right, yeah. Keyboards, etc. PCs, personal computers, they came a little bit later, and they were very much the same as the mainframes, but they introduced smaller peripheral devices, for example, floppy disks. You may have seen some of them. But today, smartphones are taking over the world. Smartphones and tablets. They are the most disruptive technology since the advent of television. We have billions of them around, particularly iPhones. And what can you do with them? I mean, you do the normal functions that you would do on a computer. You access email, you do banking transactions, shopping, you ask for directions, and there is more. You can also do personalized monitoring. So, for example, there is GPS tracking, which can track and learn your patterns, behavioral patterns. You can buy a gadget, which will then, by Bluetooth, send the heart rate information to the smartphone, which will then monitor your heart rate. You can monitor air quality, etc. And we can go further. If you look at a typical home, we are switching to what is known as a smart home. And this is because of the so-called Internet of Things. This is the vision that all your household appliances are connected and they are also Internet enabled. What I'm showing you here is a fridge, okay? This is a fridge, but a fridge is internet enabled. So it has a touch screen, and you can tweet from it. You can also look for recipes, you know, etc. But of course, you can do a lot more. And in fact, what you can also do is you can do smart energy management. So what I'm showing you is a picture of a thermostat. It looks like an ordinary thermostat. In fact, you'd have one in each room, and all you do is you set it to the correct temperature for each room, and then it will learn the pattern of your household, so it will track it, and it will automatically switch on and off the thermostat intelligently, for example, when you are at work. Is that a reality? Do you think this is a reality? Yes, okay, you may have heard the news. It's a reality, and it now belongs to Google, and the price tag is $3.2 billion. This is a Californian company called Nest, which was, I think, last month bought by Google. And what we also have is smart cars. So this is the car of my dream, because it parks itself. And of course, this is, you know, not like the research device, the sort of self-driving car that Google does. This is a mid-range Ford Focus, you know, a car that I would be driving myself, you know, if I could get hold of it. And of course, self-driving cars are next, only if we can sort out the regulation. So I've given you a few examples of what we see in a typical urban scene. And what I wanted to say that what this is ubiquitous computing. The term ubiquitous computing was actually envisaged by Mark Reiser, who was at Xerox at the time, and he envisaged this in 1993, just by analyzing the trends of computer purchases and what was happening. Now, what ubiquitous computing means that computers are everywhere and they have become invisible. Invisible, and they are pervasive. Now, they are enabled by the wireless technology, but they are also enabled, and maybe that's something that you are not necessarily aware of, by cloud computing. And in fact, cloud computing is what the mainframes have become. The mainframes of the 1980s have now become cloud computing, and they do service-based computing for your smartphones. So what ubiquitous computing is about doing computing but completely invisibly and without realizing that you are actually doing computing through the population of devices. And these devices are sensor-enabled. They use sensors to communicate. They are embedded in the environment. They are software-controlled, and they operate autonomously on their own. And of course, they are also often miniature. So if you have a look at this picture I'm showing you, this is actually not a full computer. This is an input-output streaming device, but what you see next to it is an actual matchstick. Okay? So what we have is unstoppable technological progress, and the devices are getting smaller and smaller, and people are already targeting nanoscale devices, for example, molecular robots and molecular programs. And 30 billion of these devices are expected by 2020. So these kinds of changes, they pose huge technological challenges. And one of the biggest challenges is that you have billions of these devices, and many of them are wearable or implantable. You know, an implantable medical device, for example. And you have very complex scenarios, and you need to track people, for example, instrument, the home with sensors. And what Niki is going to talk about is the challenge of how to then accurately localize people in a home, in an indoor situation or in an outdoor situation. What we also need is everywhere connectivity. And this everywhere connectivity doesn't just mean talking to, on a mobile phone, for example, from the top of the mountain to someone sitting at the university, but it also means connectivity into the mine, perhaps, underground, in the space. We really want and need global connectivity, and for that we need technological advances. And Niki, again, is working on magneto-inductive technologies for transmitting information underground. And more what we see is intelligent machines. So these machines do not just act in response to the task, to the order that you give them. They are actually autonomous, intelligent, and they just take over control from you. So this brings me to the question, if you think of those billions and billions devices, a typical pacemaker is one such device. The question arises is, are we safe? Okay. Why, do I raise this question? This is because these devices have software at the heart. And anyone who has used a computer before will have seen this screen. The program performed an illegal operation and needs to close. Okay, perhaps if it is an app on your fridge, it doesn't matter. But if it is your heart rate monitor, or even worse, if you are in the middle of a self-parking maneuver, then this is clearly not acceptable. Now, if you think that this is an imagined threat, then I can give you a news from last month when Toyota recalled 1.9 billion devices. Prius is the hybrid engine, and in the news they explained that this is due to software problems. And these software problems could cause the car stop while being driven on a motorway. Very, very dangerous. We are talking about really safety-critical situations. Worse, infusion pumps, programmable infusion pumps, they are devices that deliver drugs intravenously. And there was a big news item, and in fact FDA has issued a specific policy announcement in 2010, but if you look at the news, almost every year since 2010 they have been recalling more and more of these devices. Why? Because some of them had software that malfunctioned. These devices don't just malfunction because of the software. Sometimes they have user interface problems or mechanical problems, but there is a proportion of them which is caused by software malfunction. And here, 710 people have died over 5 years. So this brings me to what I work on, and in fact, the scientific challenges which mean that we have to develop completely new science in order to provide good quality assurance for embedded software for ubiquitous computing devices which are performing in a safety-critical scenario. We need better design techniques, we need better methods, for example, better testing, field clinical trials, but they are not powerful enough because testing will only show that for a specific input you can obtain the correct output, but is unable to provide you with guarantees. In order to have guarantees that, for example, for every incorrect ECG pattern, the pacemaker is able to maintain the heartbeat between 60 and 120 beats per minute, well, for this, you actually need to do a mathematical proof. And what we are doing is we are developing software which can essentially do these mathematical proofs and automatically. And the idea is that once you've done it, you have prevented the software malfunction. And also you reduce the development costs of the device. So this brings me to my final slide, and that is, I think, both for users of these technologies and also for researchers like me, I feel that we are living in very exciting times, and we have a very exciting future ahead. We have sensors everywhere, and what my field is bringing in is also techniques to better design and develop embedded software, and software that can actually take control and be safe. We have already smart homes, we'll have self-driving cars, etc., and monitoring of all kinds. But there are many, many scientific and technological challenges. So if you are a student looking for possible research directions, then there are many. I work in particular on quality assurance for pacemaker software. I showed you a picture of an implantable pacemaker. Pacemakers are quite a safe technology, but on an earlier slide I showed you a picture of an wireless, that is leadless pacemaker that can be inserted and attached to the heart through a vein. So the techniques that we are developing are going to be used for these new designs. And another aspect that I'm working on is trying to take sensing down to the nanoscale, to the molecular level, DNA level. And finally, I just wanted to say thanks to the Oxford Martin School for funding some of this work, and I wanted to also acknowledge EPSRC and ERC, my other sponsors.
Where's the mouse?
If you could have it. There we go. Okay.
Can you do? Yeah, the mouse is gone.
Okay.
Can you go here?
Yes, I'm trying.
I got it at one.
Sorry, bear with us. We have a mouse issue.
Oh, here.
Oh, there we go. Great. So, Marta, thank you very, very much for the interesting talk. My name is Niki Trigoni, and I'm an associate professor at the University of Oxford Computer Science Department, and I lead the Sensor Networks group. And today I'm going to give a talk about trends and challenges for accurate indoor localization. Marta already gave me some of the motivation for our work, the idea of monitoring people, patients in particular, in their homes. But we have a number of other motivating applications, such as, for example, being able to track people in airports for security purposes, for targeted advertising in shopping centers, for monitoring goods in warehouses, and this is just a number of, there are many more applications like that. So whereas GPS works very well outdoors, it is not working indoors. And however, there are a large number of technologies that are suitable for indoor spaces, for locating people in indoor spaces. Many of them are based on radio. So we have Wi-Fi, for example, Bluetooth Low Energy, ultra-wideband, but we also have other modalities, such as, for example, sound, light, and so on and so forth.
And there is a large interest from the research community in trying to crack this problem. And different approaches try to combine different modalities of the ones that I mentioned before. So it is a kind of a race from like the research point of view, but it is also a race from an industrial point of view. You see large companies such as Google, for example, providing indoor location services, having put together many maps, over 10,000 maps recently. In 2012, we see the formation of the Accurate Mobile Indoor Positioning Industry Alliance that consists of 22 giant companies like Samsung, Sony, Nokia, and so on. And last year, we saw quite a few startups, small companies that were often some of the most well-known ones I have here that were absorbed by Cisco and Apple, and that are using Wi-Fi for indoor location, Wi-Fi or Wi-Fi and inertial sensors. And the growing interest continues and continues, and as we see a couple of months ago, the Indoor Location Alliance had 104 members. So there is a great interest, but there is no clear solution that is a clear winner so far. And why is that? The problem is quite challenging because of many reasons. First, the indoor spaces are cluttered. So you have obstacles, you have walls, you have people moving around, furniture, and so on. And these obstacles, this clutter, makes some of the sensor measurements inaccurate, and as a result, the position estimates inaccurate. The second big problem is that there are currently existing solutions for indoor positioning that are quite accurate, but typically those bespoke solutions are typically expensive. So on the one hand, you have expensive and more accurate solutions. On the other hand, you have other applications that only want to use existing infrastructure. They don't have to worry about deployment costs and maintenance costs. But then these solutions tend to be less accurate. And in between those two extremes, you can deploy as many sensors as you like of different modalities, but then you have to worry about where you deploy them and how many of them you need. And the third big challenge is that it is very hard to assess the sensor errors because those depend on the environment. So there's a lot of variability. A sensor that could work well here might not work as well in a different part of the same building. And also during the night, it could have a different behavior than during the day. So it is very hard to measure the accuracy of each sensor empirically. So we would like an automatic way of estimating accuracy of sensors and then using this in order to address the fusion problem, how we fuse different sensor systems. So I'm going to go through each one of those challenges now and give you some highlights, a very high-level overview of the research directions in our group to address these challenges. The first one has to do with clutter, as I mentioned before. And here's a very simple example with trilateration, where you're trying to assess the location of the node in the middle, the red node, if you know the locations of some fixed access points and by measuring distances to them. And in the absence of clutter, distance measurements tend to be quite accurate, so they only suffer from small Gaussian errors. However, in the presence of clutter, you can find some distances being contaminated with large positive errors. These non-line of sight errors that I denote here with n, lowercase n, are quite detrimental. Because here's another example, for example, with 8 anchors and the node in the middle that wants to locate itself. If even 3 of those anchors, you have distance measurements to them that are very inaccurate, suffer for very large errors, as you see on the right-hand side, then using traditional techniques like least squares optimization, you're going to get estimates that are quite far away from the ground truth. So the question that we asked is, are we able to find those error measurements, those large errors in the measurements? And if we can find them, then we can correct them and we can localize easily. It turned out that we can do that in certain scenarios using the theory of compressed sensing. And what are these scenarios? the scenarios that agree with the assumption that most of our distances are pretty accurate, but only a small part of them have these large errors. If this is the case, then we can use we can phrase our problem as a basis pursuit denoising problem, and we can identify this vector of large errors n, which we assume is sparse, so most of the elements of that vector are 0. But if we make this assumption, we can estimate very accurately, and these are the red bars over there, which are those errors. We can correct them, and then we can use the corrected distances to robustly localize the node in this cluttered space. The problem this is just one simple example of signal processing technique that you can use to mitigate errors. But the problem is that it makes limiting assumptions. What we are in a cluttered environment where we don't have this assumption. In this case, we're taking a different approach, and we say, instead of dealing with the problem, what about completely avoiding the problem? Turning to a modality such as low-frequency magnetic fields that penetrate walls, furniture, people, air, water with minimal attenuation, and do not give us these large distance measurement errors. So Andrew Markham started working on this in our group a couple of years ago, and we continue to work in this area. He built this transmitter, which you see up there, which has triaxial coils, and is generating rotating magnetic fields. And Tryon, who is also at the audience, is started working in this project recently. And the receiver is basically sensing the magnetic field, and based on what it senses, it is able to tell its position in 3D. The signal power decay with low-frequency magnetic fields follows the inverse cubed law. So the signal decay is very fast, which means that the range is quite small. And if we take a transmitter and a receiver outdoors, we see a very nice relationship between the signal strength on the y-axis and the distance on the x-axis, which follows the theoretical free space model. Now, you take a transmitter and a receiver indoors, you see quite big problems. So you see bad news, which is basically that the free space model here does not agree with the model that results from the data. But the good news is that this model is pretty good at allowing us to predict what the distance is from the transmitter given the signal strength that we measure. So, although the magnetic field indoors is distorted and creates some problems, the field is very predictable. So we can go to an indoor environment that we're interested in, and we can take some measurements of signal strengths at various locations, estimate expected signal strengths in the remaining location using interpolation, and build a map like the one that you see over here, of where the transmitter here is at the bottom left corner, and you see the expected signal strength of the receiver in various positions around it. And you may ask, well, can't we do the same with other type of signals, such as Wi-Fi signals? Can we just not build Wi-Fi maps and use them to localize? You can, and many people have done that, but the key difference between the two modalities is the fact that the magnet-inductive received signal strength is very, very stable over time. So here you see an example where the magnetic transmitter and receiver are indoors, and people move in between for a period of about 8 minutes. And you see, in stark contrast, the RSSI of Wi-Fi, which varies quite a lot over time. We are able to exploit this property in order to localize people with this new modality quite accurately, with an accuracy of tens of centimeters, and exploiting the fact that the field is stable over time, even in the presence of moving people. But then you might say, oh, well, yes, but this requires your transmitter to be put somewhere in my building. So it requires infrastructure. What if I want to do indoor localization just with existing infrastructure and not add any additional hardware? So the next part of the talk, I'm going to focus on popular techniques and techniques that we are developing in our lab for exploiting existing infrastructure. What is existing infrastructure? First of all, Wi-Fi access points. They are ubiquitous nowadays. They are available in most buildings, and they can help us localize ourselves. Second, everybody has a smartphone, or pretty much everyone has a smartphone. And the smartphone has inertial sensors, a gyroscope, accelerometer, magnetometer that allow us to measure our relative motion. And it also has Wi-Fi, Bluetooth, low energy radio. And in some buildings, such as airports, museums, and so on, we also have CCTV infrastructure. So how can we use these existing infrastructure? We start from a very simple step with inertial tracking. This means just use our smartphone and nothing else in the building. The smartphone, within its inertial IMU sensors, allows us to find our relative motion compared to a starting position and orientation. However, the problem with that is that the inertial trajectory that we estimate, which is the blue one over there, starts drifting further and further away than our true trajectory over time. So, in order to address this problem, we can merge inertial tracking, combine it with radio data. So what we can do, for example, is if we have estimated two inertial trajectories, and these two nodes start exchanging radio beacons, when they start hearing each other's beacons, they know that they're quite close to each other. So instead of thinking, initially they thought they were at large distance d prime, but now they hear the beacon, they know that they're closer and they can correct their inertial trajectories. And this can be basically, you can see here an example where proximity constraints using Wi-Fi can be exploited between mobile nodes and fixed access points, or between mobile nodes themselves. And these proximity constraints, as well as the motion constraints that we get from the inertial data, from one person and from the other, and knowledge of the location of the access points and the distances between access points, can all be combined as constraints in order to localize people indoors. And this is a very popular technique, and different groups around the world have used it, and they have applied different kind of techniques to fuse data from Wi-Fi and inertial, such as extended Kalman filters, hidden Markov models, particle filters, and so on. And we can get reasonable accuracy. We can get accuracy of about 1 to 3 meters, which is pretty good. However, in places where it is important to know our location even more accurately, for instance, for security reasons or in museums when you need to get information about an exhibit, you might want to also exploit further existing infrastructure. And in this particular case, I'm referring to cameras. So you might have CCTV infrastructure, you may have cameras already in the building, and you can exploit this information to improve tracking accuracy. To give you an example of how we do that, I will use an example of an experiment that we did in the Pitt Rivers Museum, where we have Savas here, who's at the audience. He set the whole experiment up. We had several people moving with our smartphones, sensing the Wi-Fi signals from several access points. And we had the camera on the 3rd floor, which basically could help us to visually track people. But this was a very challenging environment because the visual detections were very far from perfect. You had detections that were empty, no people in the blob in the middle over there, D4. It was just a moving shadow. We had other detections where 2 people were in the same detection. And as you can see here, based on color or appearance alone, it is very difficult to distinguish between different people. It is difficult to identify that this is Marta and this is Niki, for example. So in practice, the tracker output, just based on visual data, was very noisy. We had interrupted trajectories and ID switches. So the approach that we used was the following. We said, okay, we can use vision, but we don't try to resolve ambiguities with vision. Whenever vision whenever it's obvious from vision, we can connect certain visual detections together into small tracklets. But as you see here, you have two people, one following T1 and one following T2. When they meet, there is ambiguity. Just using vision, we don't try to resolve ambiguity. So we interrupt the tracklets and start building new tracklets, T3 and T4 here, and so on and so forth. In the second step, then, we bring Wi-Fi in. And we use Wi-Fi in to try to identify which is the most likely combination of trajectories that correspond to my motion. And I know, because I used my Wi-Fi whilst roaming through the museum, I know what signal strengths I measured during my trajectory. And I know that if I'm moving away from an access point, my signal strength should decrease. And when I'm moving close, my signal strength should increase. So if I try to plot together my log distance, which I get from the visual detections, and the Wi-Fi that I receive, I should expect to have a reasonable radio propagation model where the Wi-Fi signal strength decays linearly with the log distance. This is the most likely trajectory, which corresponds in this particular case to the true trajectory. Other trajectories, if we combine tracklets differently, we get very unreasonable, very unlikely propagation models that could not hold in practice. Here's an example where on the left-hand side you see many tracklets that are determined based on vision, and then if I have my Wi-Fi data, the one that I collected in the museum, I can find which of those tracklets should be combined to determine my location. And as you see, this is the red estimated trajectory is very close to my true trajectory, the green one on the right. So preliminary results on real-world data show that if we combine Wi-Fi and visual tracking, we have a very promising technology, and we can uniquely identify and accurately track people under long-term occlusions, and even when appearance features are not very informative. So far, I've given you a few examples of how you can fuse different modalities. You can fuse Wi-Fi with inertial tracking, or you can use Wi-Fi with visual tracking. But what I haven't said so far is that in order to do that properly, you need to know the errors in the different sensor systems that you are trying to fuse. And these errors, so the last part of my talk is going to focus on how you assess these sensor errors and how you can use them to fuse sensor data. The motivation here I want to give you is that if you're moving in an environment and you have two different sensor systems to monitor your position, the green one and the red one, and your actual ground truth trajectory is the dotted line here, what do you notice? You notice that on the left part here of the building, a green one is more accurate, but on the right-hand side, the red one is more accurate. So wouldn't it be great if we were able to dynamically switch from one location system to another, depending on its error? So in order to do that properly, we need to be able to estimate errors, to know which one is more accurate where. And we cannot do that properly just by trusting the sensor system. For example, in this particular case, we have a location service where the true trajectory, which are the dotted, the points, the black points, it gives us a location estimate and an uncertainty bubble, but we are found outside this uncertainty bubble. And on the right-hand side, you see two competing positioning systems. One is very optimistic, the brown one. It says, oh, I'm very accurate. The other is pessimistic. It says I am less accurate. But in fact, it turns out that the true trajectory, which is, again, the black points, is closer to the pessimistic positioning system. So we cannot trust this brown system just because it says it is more accurate. And evidence from experimental data in our department in installing 3 different positioning systems on the 4th floor of the department shows that these 3 positioning systems, now I present them as black boxes, have different accuracy in different parts of the building. So the first one is accurate on the bottom left part, and the second is more accurate on the top right part, and the third one is more accurate on the top part. So what you can see here is that by employing learning and inference-based techniques, we're able to identify their accuracy and being able to dynamically switch from one to the other. Use the red one over here, the blue one there, and the blue one when we are going to the top of the building. And if we can switch between different position systems in a smart way, then we can position ourselves in very accurately. So if we trust the learned accuracy from our techniques, we get much smaller position errors than if we trust the accuracy reported by the positioning systems themselves. But is it is just being able to switch from one system to another is a rather naive solution. If you have access to all the systems, what ideally you would like to do is be able to fuse data from all the available systems that you have. Most existing solutions for fusing data over time rely on graphical models that are directed in nature. So what you see here in these models, here you see a hidden Markov model. You have states at the top and measurements at the bottom. And you evaluate the joint probability distribution of your trajectory and your measurements by just multiplying those probabilities that you see on the right-hand side. Where do you think I am at the beginning, my prior, and then you take into account what's the probability of transiting to a next position, and you also take into account the measurements. We are exploring recently in a group an alternative approach which uses undirected graphical models such as CRFs, conditional random fields. And the big benefit of this new model is the fact that we do not only associate observations to a state. We do not only say that the observations at a particular timestamp depend only on the state at that timestamp. We are able to link a whole sequence of observations, what I show here as Z, with a state or with a transition between states. This new approach, based on conditional random fields, allows us to deal with very, very noisy data. So what I'm showing here is the results of some experiments that do not use Wi-Fi, do not even use the gyroscope in your phone, just use the accelerometer and the magnetometer. And you're able to see that even with very tortuous trajectories, the trajectories that we estimate are very close to the ground truth that you see in blue color. And we've done such experiments in offices, but also in a museum, and the Ashmolean Museum and the covered market in the city center. So I have tried, to summarize, I have tried in this talk to introduce you to the main challenges that we are addressing in trying to localize people in indoor spaces, and some of the key approaches to dealing with those challenges. And to summarize, with respect to dealing with clutter, we either use signal processing techniques to remove error, or use new sensor modalities that do not give us those errors at all. We try to make the most of existing infrastructure. We try to make the most of Wi-Fi access points that exist in buildings, smartphones, and camera data if they are available. And finally, we try to accurately assess the error characteristics of the sensors in the environment using inference and learning techniques, and to explore and play with different graphical models for how to best fuse the data that we get over time. Thank you very much. I would like to thank very much all the people that basically led this research. I was just the supervisor, and EPSRC and Oxford Martin School in particular for kindly supporting us in this research. Thank you.
Can I just get a sense of how many questions that we've got, and then I can work out how many rounds of questions we might have if you put your hands up. Okay, so if we start at the back and then come to these two gentlemen here. Sorry, Vincent.
Sorry. Okay, Vincent Muller. I wasn't really prepared to start, but never mind, I'll start. I noticed that in your discussion there was a certain blindness towards anything that's not sensors. Similar problems to the ones that you've been discussing occur in robotics, and robotics people quite often use what's called SLAM, simultaneous location and mapping. The mapping part was the part which I was missing. So some of the stuff, for example, that we saw, there were these trajectories that went through the walls, and obviously what you would normally do is would say, okay, that's wrong because it went through the walls, that can't be true, so I'll throw that out. So is there some way for your systems to actually take that kind of data, which is not sensor data, into account, or to generate that data through the sensor data and establish that here's a wall, here's some other obstacle, and so the person can't be there?
Yes, that's a very good question, actually. I forgot to explicitly say that in our position estimation techniques, at least the last one that I mentioned, the Mapcraft approach, that uses undirected graphical models, we assume the presence of a map, a floor plan, and so exactly what people do in robotics, when you have, if you use, for instance, a particle filter, if particles hit a wall, then these particles are culled, and then you basically replicate, you resample over the remaining particles. We do the same, we also use floor plans as constraints in the Mapcraft algorithm. But we are not only limited to floor plans. We can use any kind of map that we have available for the environment, like magnetic maps or Wi-Fi signal strength maps. And we are also comparing with SLAM-based approaches. So yes, we are very much aware of the robotics side of things.
Thanks. Just a quick question on, I guess, what happens next. So both your presentations were very much about the technology and the accuracy and trying to get it right. But I'm interested to know whether there's been thought on your part as to, once this technology is powerful enough to put into practice, what happens, who's using it? I know you mentioned stuff about security in airports, but is there anything you can elaborate on in terms of where you see this type of technology living, how people can benefit from it, how people may not benefit from it in terms of security, government, people watching you, stuff like that. So.
You want to start?
Well, I think, so I think I showed a very broad range of technologies, and I think there are huge benefits, but as I tried to also explain, there are huge dangers, and I think we need better methods, for not just verifying embedded software, but also generating software which is correct by construction. And I think this is where my area is moving to. And it's also something that probably shares something with robotics, because this is also known as controller synthesis. So yes, but there are, of course, huge potential dangers. I mean, if you try to develop a nanoscale sensor, DNA sensor that you want to ultimately send into the bloodstream in order to, detect the sugar levels. There is a lot of work that has to go in, and I don't mean just computer scientists' work, engineers' work, but there also have to be clinical trials and, similar techniques before this gets formally approved. But I think localization has very specific.
Yes, there are a number of applications that could benefit from this kind of accuracy. For example, I was talking to a GP the other day, and he was interested in patients that have diabetes and how their motion is impaired by their condition. And he was saying that it is not just important to take measurements of health data, but also to understand exactly the context in which these measurements take place, where the people are whilst they have a certain, their vital signs are being monitored. Also with patients that have, say, dementia, they are sometimes using objects in ways that we wouldn't potentially use them. And it is important, for example, if you're able to stick a sensor on your mug and you see how the person uses them to pour water into the mug and so on. This kind of level of accuracy can increase our understanding of the evolution of conditions of this type. And another another application that has a large market behind it is basically targeted advertising. So the idea that you go to a shopping mall and your smartphone knows exactly that you're looking at this pair of jeans, and they can give you an offer about this pair of jeans and not the one next to it, requires high accuracy. Other people that have contacted us for that are people that are interested in security in power plants, including nuclear power stations. And they're interested in knowing that if something goes wrong, to know exactly where people are. And of course, monitoring products and warehousing applications have a big... So there is a large number, and it is important to get the accuracy, to sub-meter accuracy, to be able to deal with these applications.
Their own Wi-Fi hotspot, and all of a sudden the radio environment changes. Do these sort of systems, can they adapt in real time to that sort of interference?
And this is a very, very good question. To what extent you have temporal variability in a particular building, for example, this depends very much on the kind of sensor modality that you use, and some exhibit more of that than others. We are developing techniques that try to estimate the parameters of not just use fixed parameters for the algorithms that we use, but try to learn those parameters dynamically by taking into account the likelihood of the trajectories that we estimate. And so there is a feedback loop there where we are trying to estimate parameters of our algorithms, then see what is the likelihood of the trajectories that we're evaluating, and based on
there seems to be a bit of a tension between the vision of the Internet of Things, where every appliance is a sensor and networked in some sense, and perhaps the technical challenges of standardizing across different sensor systems and assessing error across different sensor systems, as well as the user experience. Maybe most of us are perhaps in the habit of carrying a smartphone constantly, but how many sensors will be too much for the users to handle? Do you see a convergence or a divergence of devices, or perhaps at the standardization level, the protocol level, or perhaps at the software level? Will we see convergence or divergence across any of those?
I think it has to happen. Standardization has to happen. We are not there yet, and we don't know when, we will get there, but it's just inevitable. I think, given the price of these devices going down, I think we have to have standardization. So, I'm a scientist. I think so is Niki. I develop software technology. She's developing different kind of technology. But of course, here we have the whole of the commercial world, and they have to contribute. And we have, for the internet, we have standardization bodies, and they also have to join in. So the whole world has to work in a connected way in order to address this problem. But I think we are still in the Wild West. As far as ubiquitous computing is concerned, it's very much the Wild West.
And I would like to add also the fact that the smartphone technology has helped quite a lot, because once sensors are able to connect to our smartphone, then everything is very easy and we can basically make sense of what's happening around us through a smartphone interface. So whereas before when a sensor network field started about 10, 15 years ago, we were only looking at modes and how they interact with each other, but then the user was outside that loop. And I see now the way that the field is evolving, everything revolves around smartphones. So for as long as these sensors can interact and connect, send their data to smartphones and the internet, then we are kind of starting to already crack this standardization problem.
I think I have like quite similar question. Like, is there like industrial standard for this indoor localization? I mean, within several years, or like within 50 years, or within my life?
I have no clue. It seems that there's a lot of interest to the extent that so many people are getting together, so many companies and so many research groups. And things are already happening quite a lot in terms of, startups being acquired. I really believe, I think that within the next 5 years, this is going to be pretty much resolved issue. Yeah.
And what do you think is the most potential technique for this indoor localization?
All of our techniques, the ones that I mentioned. I think this will probably depend on the environment and the application. The application requirements are very different, and the environmental factors are very different. So if you're talking about localization of people in power plants, you have way different requirements than localizing people for targeted advertisement. I don't think that there is going to be a unique solution, and I think that the trend is going towards fusing different sensor modalities. And which modalities you fuse and to what extent will depend on the scenario.
Do we have more questions? Vincent again.
I was sure somebody would mention the ethical problems, but nobody really did, so I thought I might do that. Sort of my job as well. It seems pretty obvious that the technologies that you're developing produce huge surveillance possibilities, and in particular that they violate the ability of the individuals to control the data about themselves. The data that the indoor localization techniques are using, for example, clearly seem to be of the sort that you're not even considering the question of whether the person who is being tracked wants to be tracked, which is different from, say, implanting a device inside me for a purpose that I have approved of and I understand the dangers and so on and so forth. So isn't it the case that some of these things that you're looking into just shouldn't be done at all?
Oh, thank you. Then I can go and rest. Yeah, this is an excellent question, actually. I want to clarify that many of the localization techniques that I mentioned actually do not compromise the privacy of individuals. So only if you install a certain application, say on your smartphone, and if the access points in and you can act as a passive receiver, so the access points in the building can send you beacons without knowing who is in there, and you can use the inertial sensors on your phone as well. So this is a simple example where you use signal strength from Wi-Fi access points and inertial sensor data on your phone, and data is not going anywhere outside your phone, and you're able to locate yourself. This is one. You could even download the map of the building on your phone, so you have no privacy issues. However, you start using modalities such as cameras, visual tracking, cameras. Then, of course, you have important privacy concerns to address. You can reduce the problem a little bit by having the cameras send you those trajectories that have no identity, and you sorting out in your phone which one you think you are. But again, you still have privacy problems there. You can potentially, someone who knows about the people that tend to go around and their motion patterns would be able to infer who is whom, right? So the privacy problems exist. In short, they don't exist for all techniques, they exist in some techniques, and they open a lot of interesting research directions about how to tackle them. But unfortunately, I'm not an expert in this area, and we're not doing research in this part. So I would not completely say no, don't do it because of that. But I see that as an opportunity for interesting research in the area of privacy.
So I just wanted to add that, I mean, privacy is a big issue even in this simple development of the Internet of Things. As we have noticed, I think recently there was a case of Google when they were sending the cars, for map data. If you have an Internet-enabled device in your home, then in theory, anyone can access it. So I think we need better techniques and protocols for ensuring privacy in those situations. And then we also need to be able to guarantee that these protocols behave correctly by, for example, mathematical proof. So privacy is, everywhere. And I think the Google example that I've mentioned of them buying Nest, which actually learns the behavioral patterns, they are already being accused by people on blogs for, trying to obtain this kind of information, because it will be very easy to infer from the particular pattern whose household it is. So I think we are not trying to duck the issue, but I think we are saying that for this we need regulation, stronger protocols.
Do we have more questions? If not, I've got one. I think just as a follow-up to that, I'd be interested to know who is it that will develop those regulations? Who do we need to look to? What sort of body is it that's going to be responsible for this?
I would hope that this would be between the governments and organizations, for example, the Internet standardization, the European,
Okay, well, I think... Sorry, I wasn't switched on. I think I'd like to thank you both very much. It's been a really thought-provoking talk, and I hope it's giving everybody here food for thought. Before we thank Marta and Niki, could I just alert you to the fact we do have one more seminar in the series, which is next week, and it'll be looking at how computerization and automation may affect jobs in the future. There's been some quite interesting work from the Future of Humanity Institute on that. And if you are interested, we do have Baroness Helena Kennedy coming to speak this evening on what we can learn from human rights, successful human rights campaigns over the years. So if you do want to come to that, please do stay on. So thank you very much to our speakers.